this course. So as physics students, you have 3 math courses, I think, 2 calculus, 1 linear algebra, and a differential equations course. But those are not really enough for you, to study physics completely. For studying electromagnetism, for classical mechanics, you need more tools in your arsenal. So that's where this course comes in. It gives you the tools that you need to study physics like more, so you have more tools in your arsenal. The first chapter, and it's going to be about vector algebra and coordinate systems. Now, you've probably been introduced to vectors before, and you've probably been told that a vector is anything that has an arrow. It's like an arrow pointing in space, and it has a magnitude and a direction. But this is something like, it's like saying that numbers are just 1, 2, 3, 4, and so on. It's like saying that all the numbers that there are in the universe are natural numbers. It's like you're ignoring √2, irrational numbers, imaginary numbers. We have to expand our view of vectors. Vectors are not just arrows pointing in space. A vector can be anything that satisfies a set of rules, and they belong in a vector space. Let's say the name of the vector space is V, and it has vectors in it. Vectors are objects in a vector space, and they follow some rules. I can summarize these rules by this equation here. If you have A and B, which are vectors in a vector space, V, then their linear combination, this is what we call a linear combination, is also in the vector space V. Okay, so these vectors can include many things. They're not just arrows. You can have triplets of numbers, A1, A2, and A3, that can be vectors. You can have a column vector that has numbers in its columns. You can also have a matrix that can be a vector in a vector space. For example, you can have an upper triangular matrix, something like this, that can also be considered a vector. You can also have functions as vectors. We'll see how this is later in the course when we study Fourier transform. And you can have many other things that can be considered vectors. So if you're restricting yourself to saying that a vector is an arrow in space, you're really, narrowing your vision. So this is what vectors are. But in this chapter, we're going to focus on vectors in space. So the vectors that like a position vector or electric field, that's the kind of vectors that we're going to study in this chapter. In later chapters, we'll see different other types of vectors and we'll study their properties. And each vector space has their own special properties. And we'll see a lot of those here. Okay, so what makes vectors in space so special? If you have seen, like in physics, if you study motion, and for example, if you study motion of an object in space, it doesn't really matter how you look at it. You can look at it from here, you can look at it from here, but the laws of physics are the same. The trajectory of this ball can be given by Newton's second law. Doesn't matter where you're looking at it from. And vectors have this property, vectors in space. So say you have a vector V like this. You can represent it in many ways. Traditionally, you'll consider a two-dimensional coordinate system like this, and you can say that this vector V has coordinates x and y. But this is not the only way you can look at this vector space. You can even have a rotated system like this. And that would still be a valid way to study this vector. The vector doesn't really care how you look at it. At the end of the day, the vector is something that doesn't depend on the coordinate. But depending on your problem, you might want to choose different coordinates because it will make your life easier. So you can analyze the problem in a much better way. Okay, so as I've hinted, to study a vector, you need a coordinate and an origin. In this case, we assume this is our origin. And a vector will have components depending on how you choose the coordinate system. So in the blue coordinate system, it has components x prime and y prime. But in the black coordinate system, it has components x and y. And the nice thing is that the vector is the same in both, whether you look at it from this coordinate system or this coordinate system. So it doesn't really matter. The vector is the same. Now, to imagine why this is, let's take an example, real life example. Suppose I have a map of Bahrain with me, something like this. You have Manama here, if you have Rafah here. So a vector starting from Rafah to Manama will be the same no matter how you look at it. Maybe you have a satellite here that is taking a picture of Bahrain and it sees the vector here. Now the satellite can be here or there, but this vector starts from Rafah and ends in Manama. So it doesn't really matter what coordinate you're choosing. You can study the vector in any way you like. And next, we want to know what you can do with vectors. Now that you can represent vectors, now we want to know what you can do with vectors. So you can add numbers, you can multiply numbers. Can you do that with vectors? And the answer is yes, you can. But before we see that, I want to show you how you can represent vectors, how we do that usually. You can represent a vector like this. Suppose you have the vector 1, 0, 0 in the Cartesian coordinate. You can represent it as a column vector. You can also represent it as a triplet of numbers like this. Both are equally valid. That's a bit of notation here, and now we'll move into vector operations. First, I want to give you a geometric view of how you add vectors. Suppose I have a vector A like this, and I have a vector B like this. Geometrically, what does it mean to add two vectors? What it really means is you take B and you put it at the head of A, and the arrow at the point at which B points is where your addition will lead you. Say that A plus B is C. C starts from the tail of A and ends at the arrow of B. This is what it means geometrically. Now, how do you know what the C looks like in your coordinate system? What you do is you have A equals A1, A2, and A3, and B equals B1, B2, and B3. If you want to get C equals A plus B, you just add the components, A1 plus A2, A1 plus B1, and I mean A2 plus B2, and so on. You've probably seen this before. Now, what if I want to know how long the vector C is? I want to find its magnitude. How do I find it? The way I find it is using something called the cosine law. This is how it looks, the cosine law. And this angle theta in this figure, it would be this theta. You should keep this in mind. It's not this one. It's the theta here between A and B. Having said that, the way you derive this equation is by Pythagoras theorem. That's a bit, cumbersome. You have to go to trigonometry. And later when we introduce dot product, you'll see a much nicer way of deriving this. That will be one of our applications later on. And now, how do you find the direction of C? What's the angle here? Let's say this is gamma. Because a vector, as you've seen before, has a magnitude and a direction. How do you find the direction here? Okay, this is given by something called the sine law. If you have a triangle ABC, and you have angles and you have the side lengths A, B, and C, You have the angles alpha, beta, and gamma. The way you get these angles is like this: A over sine alpha equals B over sine beta equals C over sine gamma. If you know the side lengths, you know the signs basically, and then you know the angles. We'll also see how to derive this as an application of the cross product. Now, don't worry if you don't know what the dot product and the cross product are. We'll see them later on. Now, this is how you find the magnitude and the direction of C. Now, the next topic we will see is multiplication. How do you multiply two vectors? You know that we can multiply numbers. So can you multiply vectors? And the answer is yes. And multiplying two vectors can give you either a scalar or a vector. When you get a scalar when you have the dot product, it's some number C. C belongs to real numbers. And if you take the cross product between two vectors, you get a vector C. And we'll see how you compute these dot products and the cross product. Let's begin with the cross product. The way I like to visualize cross product is you imagine you have a piece of paper and you have two vectors inside. You have a vector B like this, and you have a vector A like this. The cross product will give you a vector C that is perpendicular, عمودية, on both A and B, that goes either like this out of the page, just give me a moment. Okay, so that goes outside the page or below the page. But conventionally, if you're crossing A and B in this order, the C will be outside the page like this. And it's determined by the right hand grip rule or the corkscrew rule, depending on. So it goes from A to B. This is the direction of C. This is a convention that we choose in our coordinate system, that the right-handedness is positive and the left-handedness is negative. There is actually no reason for this whatsoever. Either is equally valid. Well, this is what does it mean geometrically to take a cross product? You get a vector that is perpendicular to both of the vectors, but what does the magnitude tell you? The magnitude tells you that if you have two vectors A and B, the magnitude gives you the area that is formed by the parallelogram. It gives you this area. Okay, and how do you compute C? If you have a vector A that has components A1, A2, A3, and you have a vector B that has components B1, B2, and B3, you compute C using the determinant. In the first column of the determinant, you have the Cartesian basis, I, J, and K. In the second one, you take A, the components of A, A1, A2, and A3. And in the third one, you take the components of vector B, B1, B2, and B3. Now, if you have studied determinants before, you know that if you switch the rows or if you switch the columns, you get a negative sign. That's why you know that cross B must equal minus B cross A. This is what we call anti-commutativity. We say that the cross product is anti-commutative. This concept comes up in quantum mechanics a lot. You have interesting behavior when you have something that is not commutative. Anyway, this is something that you'll see in future courses. Okay, so this is let's see some more properties of cross product. These may seem obvious to you, but you should still see them. Suppose if I have a vector a1 plus a2, and I cross it with b, I'll get the sum of the cross products like this: a1 cross b plus a2 cross b. So this is what we call the distributive property. And of course, it's a linear operation, the cross product. So if you increase the length of a by some constant c, and you cross it with b, the length of the cross product also increases with c. Yeah, these are trivial properties. And now we move on to the dot product. Now, the cross product gave you the area between two vectors. And so, you can think of cross product as telling you how spread apart the two vectors a and b are. If the vectors a and b are parallel to each other, the cross product will give you 0 because the area between a and b is 0. So cross product is a measure of how spread apart a and b are. On the contrast, the dot product tells you how close the two vectors are. So suppose you have a vector b like this and a vector a like this, the dot product is maximum. And suppose you have a vector a like this and you have a vector b that is perpendicular to a, and the dot product is 0. So dot product kind of measures like how close a and b are. Now geometrically, what dot product really is, it tells you how much of b is in the direction of a. You can think of shining a light on b from here, from the top, and the shadow of b on a is the projection of b on a. That's what we say in mathematics. And the dot product is a measure of the projection. If the projection is really large, then the dot product will be large. Now, how do you compute the dot product? If you recall the notation I introduced in the beginning of the lecture, that a vector a can be represented by a1, a2, a3 as a column vector. Similar with b. B is basically b1, b2, and b3. So a dot b is basically a1. You flip the vector, the column vector, like this. We call it transposing. If you studied linear algebra, you have probably seen this. And the reason I'm showing you this notation is because this is quite frequent, like in quantum mechanics, and you'll have to get used to this notation. And it's the usual summing the components, the product of the components, a1 b1 plus a2 b2 plus a3 b3. And the properties of the dot products are the same. If you have a vector a1 plus a2 and you dot it with b, you'll have a1 dot with b added with a2 dotted with b. This is trivial by now. Now let us look at some applications of the dot product and the cross product. And the first one that is quite familiar to all of you, I think, is work. Work is actually a dot product. If you move a particle at distance dx, let's use vector notation here because displacement is usually a vector. You'll get an infinitesimal work dw if you apply a force F on the particle d and you displace it by some amount dx. You have a force on it, F. Now, if you sum over all the forces, all the work you've done throughout the path, suppose I have a path like this, and if you sum the dw's at each instance of motion, you get an integral. And this is a special kind of integral. It's called the line integral. We'll see this in more detail in the second chapter. For now, I just wanted to introduce you to this dot product, this special dot product. And also, speaking of dot product, I promised you that I'm going to derive you the law of cosines. So we've seen earlier that if you have a vector addition like this, let me just copy this. If you have a vector C that you get by adding A plus B, the equation we got for C was something like A squared plus B squared plus 2AB sine theta. Now we can actually derive this using the dot product. So dot product also gives you the length. If you take a vector dotted with itself, C dot C, it gives you the length of the vector squared. You've probably seen this before. Now C is actually A plus B. So C dot C is actually A plus B dotted with itself. This is equal to the length of C squared. What this gives you is A dot A, which is A squared, plus A dot B, plus B dot A, plus B squared. Now, one of the properties of dot product is no matter the order, the dot product gives you the same number. So we can write this as 2A dot B. Now, if you know the angle between two vectors, theta, if you know this theta, another way you can express the dot product is like this. A dot B equals the magnitude of A times the magnitude of B times cosine theta. You may ask why cosine? Because Pythagoras, if you have a unit hypotenuse and you have a theta here, you have this side is cosine theta and this side is sine theta. Just a reminder. Now let's look at this, what the expression becomes now. So we have A squared plus B squared plus 2AB cos theta, which is equal to C squared. This is exactly what we wanted. This is what we call the cosine law. And now you know how you derive it. Now let's do an application of the cross product. An important quantity in electromagnetism is called the Poynting vector, which you will actually not see in 348, the electromagnetism course, unfortunately, but at least you'll see it here. The Poynting vector is defined something like this: 1 over mu naught electric field crossed with the magnetic field. Now, what does the Poynting vector actually tell you? It tells you that if you have an electromagnetic wave, not just electromagnetic wave, even just have two vectors, E and B, then there will be, you can represent the energy that is moving in space using you can consider this as a light wave, and you can have some area here. The amount of energy that is passing through A per unit time is what Poynting vector tells you. So it's kind of like power. Yeah, it's basically that it has the units of power. Okay, so this is one quantity that is represented by cross product. Another one that is quite familiar to you is torque. Torque is the cross product between the position and the force that is acting on the object. Okay, now let's derive the sine law now. Now, I've told you that the cross product actually gives you the magnitude. If you have a parallelogram, like this. If you have vector A here and a vector B here, this is vector A, this is vector B. And the angle between them is known. I'm sorry, this is not the angle. This is the angle. Then you have A cross B gives you the area of the parallelogram. And if you know the angle between two vectors, the cross product can be, the magnitude of the cross product can be given by this, A, B, and the sine of theta. Now, if you look carefully in the figure, you'll see that the height of the triangle is given by B sine theta. So the presence of sine here should not surprise you. Now, this is, you can take the area of the triangle in three different ways. So you can take the vector A as your base, you can take the vector B as your base, or you can even take the vector C as your base. So depending on what base you take, area of the triangle, by the way, the area of the triangle is one half of the area of the parallelogram. So you're dividing this parallelogram into two, you get a triangle. So it could either be A cross B or B cross C or C cross A, depending on which base you take. The one half cancels throughout. And so you have the remaining things here. Now let's revisit what the angles between these are. This is alpha, and this is beta, and this is gamma. Now A cross B is actually A, B, sine gamma. Okay, so it should have been gamma here, which is actually equal to B, C. What is the angle between B and C? It's alpha, as you can see here, which is equal to C, A. What is the angle between C and A? It's beta. Let's just choose any two of these equations here. So this is equal to this. B cancels out. So you have A over sine alpha equals C over sine gamma. This is actually the sine law. And if you look at the other two equations, you'll see that it's B over sine beta. This is what we wanted to prove. And now you know how you get the sine law. Okay, but this is not the only way you can multiply vectors. You can multiply three vectors together. Now we'll do triple products with vectors. Just like the multiplication with two vectors, we'll also see that we can get a scalar and a vector when you multiply three vectors. So we consider vectors A, B, and C. You'll get a scalar value when you have what we call the box product, A dot B cross C. Okay, and you get a vector when you have the vector triple product, which is usually denoted like this. And the presence of the bracket here is quite important, you see, because it matters whether you do A cross B first or whether you do B cross C first. They're not equal. And the result you get from each is different. This is one of the things with cross product. You cannot associate the operation here. Okay, so let's see how we can compute the scalar triple product. And you may or may not be surprised, to see the determinant here again. So basically, if you have A dot B cross C, the way you compute it is by having the components of A in the determinant in the first row, components of B in the second row, and the components of C in the third row. This is actually computed by the determinant. Now, what does this mean geometrically? To have something like this. If you have studied if you have seen the determinant before, you know that if I have B equals A, if I have B equals A, i.e. these two rows are the same, you get a scalar triple product of 0. What does this mean geometrically? Let's try and see this. So I have a vector A like this, and a vector B like this. And imagine that we have a vector C that is not in the same plane. And together they'll form, oops. Okay, so together they'll form a box of some kind. So you can imagine that the vectors are along a box. So you have A here, and then you have B here, and then you have C here. What the scalar triple product gives you is the volume of this box. Is actually the volume of this box that the triple product gives you. And there are applications in physics of the scalar triple product. Just today, I was doing a class in solid state physics, and we had to find the volume of a unit cell. So you know that these are not just exercises that you'll do in this course. You'll actually use them. Now let's move on to the vector triple product. So it's usually, as I told you, the vector, the bracket in between this is really important because it matters where the brackets are. While we won't see the derivation of this expression, you can read about it, but it's much simpler. The derivation is much simpler when you study tensors, which is in mathematical physics too. So if you get the chance, you should take it, in my opinion. So A cross B cross C, the way people usually remember this is by something called back cap. So you have B A dot C. The first one is a vector, the second two are dotted. Minus C A dot B. This is the formula. I won't show you the derivation because it's not going to give you much of an insight. Well, anyway, this is the vector triple product. So now it's time to move on to another topic that is quite important to physics, and that is coordinate systems. The choice of a coordinate system can simplify your problem quite a bit. So you should study the coordinate systems. Now, as I said before, for a coordinate system, the most important thing is the basis. If you know the basis, you can find any point in the coordinate system. So let's start with the 2D coordinate systems. The most famous one is the one you all know, the Cartesian coordinate system. And we'll also discuss the polar coordinate system. If you've noticed, the paper I'm writing on, or the tablet I'm writing on, has a rectangular grid. And the Cartesian coordinate is usually the most intuitive one for you, but it may not be the most useful for a problem. So you have the unit vectors I and J. So if you want to go to this point, you take 2 times I plus 2 times j, and so on and so forth. Now, one thing that you have to notice is that no matter where I go in this coordinate system, suppose I go here, the I and j are the same. They don't really change. You'll see that this is not always the case. In fact, if you go to the polar coordinate system, you'll see that the basis vectors change as you move around the space. So the basis itself depends on where you are. So let me try and show you that. For the polar coordinates, the variables you need to know are r and theta. So suppose I have r equals 1 here, it's a circle. R equals 2 here, r equals 3, and so on. And theta, you have theta equals 0 here, theta equals 1 in some units. Maybe theta equals 60 degrees, 90 degrees, and so on. Now, what are the bases here? How do you define a basis? I mean, you took for granted the basis I and j in the Cartesian system. But now, what are the basis vectors in the polar coordinate system? The way I think of it, the basis, is I keep everything constant. I keep y constant, and I only change change x. What is the direction of a vector of a position vector when you only change x? It's in this direction, right? Because y is constant, so you can only move along x. So the direction of I must be in this direction. Also, the basis here is orthonormal. Orthonormal. Orthonormal basis is quite convenient to use because you have the magnitude of I is 1 and I dot j is 0 because, you know, the direction between the angle between I and j is 90 degrees, so it's orthonormal. And you can also construct an orthonormal basis in the polar coordinate system. So you have, okay, let's imagine that you fix theta at theta equals 0, so somewhere here, and you only increase r. If you increase r, so basically you have r equals 2 here, maybe you want to go to r equals 3. So the basis vector will be pointing this way. This is ER. ER meaning it's a unit vector in the direction of r. Now suppose I fix r and I increase theta in certain directions. I mean, you're only allowed to change in the direction of theta. If I fix r at 2 and theta is changing like this, E theta must be in this direction. If you increase theta, you'll go here. So the direction is tangent to this. Then again, ER and E theta are perpendicular to each other, so they're also orthonormal. Now, ER and A theta are not the same everywhere. Suppose I choose a point, say here. If I increase R in this direction, keeping theta fixed, say theta is 90 degrees here, I'm fixing theta. I'm only changing R. The direction will be here. But this here is not the same as this. At this point, you have the ER pointing this way, but here it's pointing in some other direction. And the same with theta. Here you have, if you fix R over here and you increase theta, you're moving in this direction. One thing I have to mention is that, you know, when I say I'm increasing theta, I'm moving counterclockwise. There's another convention like that was just decided. There's no real, you know, you just stick with it. Okay, so how do you move from this coordinate system to this coordinate system? Suppose in the Cartesian system, I have coordinates x and y. How do I move to r and theta? What's the relation between them? If you've probably seen this before. Suppose I have this Cartesian system, x and y, and I have a point here that is at x, y, small x and small y. And I have theta here. This is a right angle triangle. And this is r, the radius of the circle. You can imagine that there is a circle in here at some point theta. You know from the Pythagoras theorem that, or from trigonometry, that x equals r cos theta. X equals r cos theta. And y equals r sine theta. This is how you move from xy to r theta. Now, how do you move from r theta to xy? So now I know this point is r theta. And I want to know what are the coordinates x and y, these distances. Now you use Pythagoras theorem, or again trigonometry, however how you like it. Now no, it's actually Pythagoras theorem, isn't it? It's x squared plus y squared equals r squared. And from before, if I divide these things, what will I get? You'll see that r and r cancels out. And the resulting equation is x over y equals 1 over tan theta. Because cosine over sine is 1 over tan theta, or cotangent. So you can find theta as tan inverse of y over x, I'm sorry. This is how you move from r theta to x and y. Now there's a more systematic way of doing this that we'll not see in this chapter, but we'll see it in the next one. It's called the Jacobian matrix. I'm not sure if you'll actually cover this in your course, but you have to see it. You know, it's a systematic way of moving from one coordinate system to another. You may be given a really awkward coordinate system that you've never seen before, and you'll still be able to, move between Cartesian and that coordinate system. That's what we call a Jacobian of the transformation. Also, I want you to note another thing in these coordinates, like C. You have this area element, right? This area element changes as you move away from the center for the polar coordinates. But here you can obviously see that these squares are all the same shape. So this is again related to coordinate systems. Like if you change coordinates, you're not guaranteed that your area element will be the same. And we'll see this in the next chapter. Okay, so I think we've seen enough of 2D coordinate systems. Now we'll move on to 3D coordinate systems. Okay, so we'll start 3D coordinate systems. But let me take a moment to ask if any of you have a question so far. Any questions? No. Okay, so let's continue. In 3D, for 3D coordinate systems, we're going to study the Cartesian coordinate system again, and we'll study polar coordinate system. But now, choosing a polar coordinate system is not unique because you have two types. You have the cylindrical one and the spherical one. But first, let's just quickly see the Cartesian system again. You have x here, you have y here. You can imagine that from the right-hand rule, z must be perpendicular to both of these. So this is a plane, and this is going outside of the plane. And again, you have the basis vectors I, j, and k. And these basis vectors don't change as you move around the space. You go here, I is here, j is here. and k is here. Same thing here, and so on. This should be familiar to you. Now let's look at the cylindrical coordinate system. The cylindrical coordinate system is just an extension of the polar coordinate system that we saw here. So you have this r, theta. You simply add z here. So what it looks like, it's like this. You have a z-axis pointing out. And so you'll have cross sections like this. This looks messy, so I'll just delete this. Let's look at the basis vectors in here. But first, let's look at the variables that you have, r, theta, and z. The basis vectors are the same again. If you suppose I want the theta here, I fix r. I only increase theta. And you can see that theta will increase in this direction. Now if I fix theta and just increase r, you'll see that r points in this direction. This is ER. This is E theta, right? And now z would be the usual z, the k hat vector that you see. This is z hat. Okay, but now let's look at what happens when you change this point. So instead of taking, say, this point, I move here. Now you will see that the basis is no longer the same. If I increase theta here, to point in this direction, this is A theta. And ER, if you change R, it will point in this direction. Now compare it with this one. This is pointing to the right, this is pointing backwards. And so, but Z, you can see, the Z didn't change. The Z unit vector is the same. Again, these are all orthonormal coordinates. So ER has unit 1, so does E theta, so does E phi. And if you take the dot product between any two different bases, you get 0. And this is nice. Now, the conversion is similar. I mean, I can literally just copy these conversions and paste it here. The conversions are the same as the polar coordinates. You just take a z equals z here. So the cylindrical coordinate, here you have it. Now we'll move on to the spherical coordinate system. Now things get a bit different. You see, you have this, let me draw the Cartesian coordinate, just for reference. This is x, this is y, and this is z, right? Now what you have here, you should imagine a sphere here. So in the spherical coordinates, your variables are the following. You have r, theta, and phi. I'll go through this really carefully here. Before, in the cylindrical coordinates, r was always in this plane. You never had r like this. R was always in the, you can say, xy plane. It never went in the z. But in the spherical coordinates, you do have r like this. You can in fact have r like this. R can point this way, R can point that way. R is no longer restricted to a plane. It can be anywhere on the surface of the sphere that you have here. It can be anywhere on the sphere. So that is something that you should keep in mind. And now let's focus on a point in the sphere. Say I fixed theta and phi. I haven't defined theta and phi yet, but say that I have a radius along here, and I fix everything else. I just increase r here. Where will the vector point? You'll see that the sphere is pointing, the arrow will point outside here, because if the sphere is increasing in its size, the basis will point like this. This is ER. Now, what is theta? The conventions actually are not the same everywhere, but I believe your textbook uses this convention. You take an arc immediately from Z. Theta equals 0 implies you're in the Z-axis. This is theta equals 0. If you move along here, if you increase theta, you're moving from up to down. Suppose you're living on the Earth. This is the Earth. You know, you have the North Pole here, you have Asia, Africa, Bahrain somewhere here. You're moving from the North Pole, which is theta equals 0, straight down somewhere here. This is what theta is. Okay. Now suppose I fix r and I fix phi. I'm only increasing theta. So you can imagine that theta will increase in this direction. So the unit vector of theta must be here, this blue one, and it's perpendicular to the r vector. Because why is that? Because the unit vector of theta is tangential to the sphere. Okay, let me just erase this. Okay, now let's look at phi. Now phi, you can imagine, suppose I have an orange fruit in here, and I take a slice out of it, like this. If you're looking at it from the top, you'll see something like this. Phi is called the azimuthal angle. So phi equals 0 will be along the x-axis. This is phi equals 0. If you increase phi will increase like this, exactly like the polar angle that you saw before, exactly like theta in here. So the theta here is phi in the spherical coordinates. Anyway, turns out the orange will have to go. Well, now let's imagine, like, at this point, I'm increasing theta. I'm fixing theta and r, and I'm just increasing phi. Now, again, if you return to the Earth's coordinate system, and you take a slice like this will be like increasing phi like this. Phi equals 0. Phi will move along here. So as you can see, if you move up, this circle gets smaller. Anyway, that's just for you to visualize. So the phi here, if you think about it, will point into the page. Okay, so here's another notation. If a vector is pointing, if you imagine this is a vector, okay, if it's pointing into the page, you're looking at the tail of this, and the tail, people decided it looks like this. And if this vector is pointing outside of the page, you're seeing the tip of the vector, and they decided it looks like this. This is just a convention that I'm pretty sure you've seen it. And so if I draw the three, at this point, if I draw the three bases together, you see that E theta is like this. This is just zooming in here. This is just zooming in. . Okay, so you have ER pointing perpendicular to this, and phi is pointing inside here. Okay, I hope this makes sense. Now, I should comment again that if you move across the sphere, these bases will not be constant, like I, J, and K. Like in the Cartesian system, if you move anywhere, these I, J, and K are constant. But with the spherical coordinates, ER, E theta, and E phi will not be the same. The direction of ER, E theta, and E phi will be different. But one thing that will be the same is that they'll all be orthonormal. So if you have ER dotted with E theta, you get 0. If these vectors are different, you'll get it 0, and they're all unit vectors again. Now, how do you move between coordinates? Like, if you know the point, suppose I know a point x, y, z, and I want to know how it looks like in r, theta, and phi. Now, doing this will need a bit of imagination here, and I'm not that great at drawing, but I'll try my best. Now, r, what's r? If I have this sphere, and I have r pointing from the center outwards. So I have r pointing out like this. You can intuitively tell that, if you have a point from the origin, 0, 0, 0, and this point is x, y, and z, the distance from 0, 0, 0 to x, y, and z is r, the radius of the sphere. But it's also x squared plus y squared plus z squared. Again, this comes from the dot product, if you remember. Suppose this vector is not small r, but capital R, to differentiate it from the radius. Okay, so r will be equal to the square root of capital R dotted with itself, which is basically this. Okay, so how do you find theta? Now, if I take a cross section of this sphere, and you have theta here, so how do you find theta? So all you can tell is that this is theta equals 0. You have r here, and this is theta. Now, if I take the projection, the dot product from here to here, now this is the z-axis, you should remember here. The z-axis is pointing out like this. As I said, theta equals 0 means that you're along the z-axis. This is actually the z component in the Cartesian coordinate. So you have this r, and if you take r in the k direction, you'll get r cos theta. That's how you find z. And so theta will be equal to z over r. The cos theta will be z over r. That's how you find theta. Now, finding phi. Phi is as I said, phi will be in the xy plane. So if you have this xy, and you have it won't necessarily be in the xy plane, because you can move along the sphere, you can move upside above the sphere, and you'll have a smaller radius, a circle of smaller radius. So, for example, if I'm at this level of theta, what is the radius in here? Now, the z was given, the z component was given by the projection, right? R cos theta gave you z, so this will be r sine theta. Make sense? So the radius of the circle in general is r sine theta. Okay, so what did I want to tell you here? Phi, right? So you have this point. X, Y, z. Now, z is r cos theta. X is r sine theta. Like, see, now I remember what I wanted to say. This is the radius here is r sine theta, right? So this is phi. I know these components. How do I know them? By trigonometry. So if I take this radius, let's call this r prime, this r sine theta equals r prime. The x is basically r prime cos theta, and y is r prime sine theta. Just replace r prime with r sine theta. What will you get? X equals r. Oh, I'm sorry. I should have written phi here, because this angle you see here, it's phi. So these should be cos phi and sine phi. So now I substitute back the r primes here, which is r sine theta, cos phi, and y equals r sine theta, sine phi. And z, as we saw, is r cos theta. This is how you move from the Cartesian coordinate to the spherical coordinate. And the reverse is not really important. I mean, you can look them up. It's not really that important to us at this point in the course. And so we've introduced all the important coordinate systems. Now I want to talk a bit about coordinate transformations now, because you might have a coordinate system that is not familiar to you, but you might still want to move between the coordinates. How do you do that? Also, I've told you that I've hinted at in the beginning of the lecture that vectors are actually rotationally independent. Like, if you choose a coordinate that is rotated somehow, but the vector is still the same. So I want to explore this a bit. So we'll start with rotated coordinate systems. Okay, so suppose I have some coordinate system x and y. And suppose I have a different coordinate system that is just rotated. The origin is still the same. You have y here, y prime here. You have x prime here. You've just rotated this by some amount. And suppose I have a vector, just a vector here, called v. Now, the basis, let's talk about the basis here. You have, for this unprimed coordinate, you have I and j. For the primed coordinate, you'll have I prime and j prime. This should be along the x prime axis, so you'll have I prime and j prime. Now, depending on the coordinates, the representation of v will either be xi hat plus y j hat, or it could be x prime I prime plus y prime j prime. But they're still the same vector. These are the same vector here, you see. This vector doesn't really care about which coordinate you're looking at it from. This vector is the same. Now, what if I dotted I with v? What would happen? Let's imagine that I dotted I here on both sides. What would happen is that you'll get x I dot I plus y j dot I. I dot I is 1, j dot I is 0. So I dot v gives you x. Similarly, if you dot j with v, you get y. So now you can see that if I want a component of the vector along x or along y, I just dot it with the unit vector along that direction. So same thing with the primed coordinates. If I want x prime, I'll just dot it with the I prime. And same here, j prime. Right? Now let's see. Suppose v, I take v to be xi plus yj. And I know from these equations that if I dot I prime with v, I'll get x prime, right? So you'll have x I prime dot I plus y j dot I prime equals x prime. Similarly, if I dot j prime with v, I must get from here y prime. Now what will this be? This is from the coordinate system. I want to remind you, like xi plus yj is in the unprimed coordinate system, this one, the black coordinate system. And the primed one is this one, the rotated one. I'm trying to find an expression that will give me the components of x prime, y prime, given I know the components in x and y, right? Similar to what we did here. We knew x, y, and z, but we wanted to know r, theta, and phi, like depending on the coordinates. So I'm trying to find an expression that will give me the rotated frame components. So that's our main goal here. So I'll have j prime dot I plus y j dot j prime. That's going to give me y prime. Now, if I look at these two equations, this one here and this one here, I can organize them in a matrix. If you've taken linear algebra, this would be quite familiar with you. Like, what I mean is that these dot products here can be the components of a matrix. They're the elements of a matrix. So let's look at it like this. I prime dot I, j dot I prime. This one, these are the first two elements. And then I have these two elements, which are j prime dot I and j prime dot j. Let me write this. Let me just erase this. I want to write it in the same way everywhere. So I prime dot j. So if you look at this closely, let me just complete this equation first. X and y will give you x prime and y prime. This is the equation that we want at the end of the day. This is how you move from xy, from the unprimed coordinate system, this one, to the primed coordinate system. You know this, you want to find this. Okay, so usually what will happen is that you'll be given these basis vectors, right? Or you can just, if you know the angles, right? Like you know the angle between I prime and I. If I know this angle here, this is I prime, this is I. If I know this theta I, then I prime dot I will give you cos theta I, because this is unit vector, this is a unit vector. So I'll get a cos theta I here. Similarly, if I know the angle between these two, let's write cos theta I, because we have two i's. Then cos theta ij, cos theta ji, because you have dot product between j and I. And finally, cos theta jj. Usually you'll either be given these vectors, these component vectors, or you'll be given these thetas, right? Anyway, let me just erase these stuff. And depending on which one you're given, you can easily compute these rotated components, x prime and y prime. So we have 5 more minutes left, and then I'll finish this lecture. I'll just generalize this to 3 dimensions now. The 3-dimensional transformation is basically the same. You just have one more component here. Like, let's look at the structure of this. Like, in the first row, you have I prime dotted with I prime dotted with j. So those components will still be the same. I prime dotted with I prime dotted with j. And then you have I prime dotted with k here for the third component. And then for the second row, you have j prime dotted with I, j prime dotted with j, and j prime dotted with k. And in the third row, you'll have k prime dotted with I, continuing the pattern, k prime dotted with k, dotted with j, and k prime dotted with k. And then you'll have the xy here, xy and z here, and this will give you the rotated system here. Again, if you know the angles between these components, you can substitute the cosines here. Otherwise, if you're given the vectors here, you substitute with them. There's probably an expression that gives you something like cosine theta here, cosines everywhere. You can look that up if you want, but this is the derivation of that equation. You'll probably not be asked a question like this because it requires that you memorize. Well, you don't really have to memorize. You just have to remember this pattern here, primed with unprimed, and it repeats like this. And now I want you to think about this a bit. Think about this equation a bit. What we're seeing here is a linear transformation. That's a big word, linear transformation. What does that mean? What it means is that you can imagine this matrix to be like a function that takes in a vector v like this, and it gives you another vector v prime. Now v prime is a rotated vector. For example, like suppose I was in the xy coordinate here, and then I moved, and then I switched my face. I just looked the other way around. So the v will not look the same to me. I mean, because I've moved like around v. So the components of v look different to me now. You see? Let me just draw the components here quickly. This is the component when I was in x and y coordinate system, and this is the component when I'm in the primed coordinate system, right? So this function is going to tell me what the new components are. So this is an idea that you must keep in the back of your head. Like, matrices don't just, they're not just some notational trick. They're actually like things that act like functions. And this is where I am concluding my lecture. I just wanted to say that linear algebra is really important. I mean, if you're studying physics, a lot of the things that you're solving, like differential equations, different systems of equations, vector spaces. I mean, a lot of it depends on linear algebra. So you have to focus on linear algebra when you take it. And thank you very much for attending. I guess that's it for today. Okay, so do you have any questions before we leave? All right then. I'll see you next time.